Good morning, good afternoon, good evening, wherever you are. Happy learning. This is your Professor Atifreed Muhammad. We will be discussing in quite detail today on AI models. Artificial intelligence models are mathematical and computational representations that simulate the behavior of intelligent systems. These models are designed to learn, reason, and make decisions based on the data they process. Let's look into that together. We will be discussing quite a few models today, but before I go into the autoregressive models, let me share a little bit more on AI models and why they are significant. AI model is a neural network in major, that's what we have as humans, which is inspired by the structure of function of the human brain. Neural networks consist of layers of interconnected nodes or neurons that process and transmit information. Deep learning is a subset of neural networks that gained significant attention in recent years due to the ability to achieve state-of-the-art results in various tasks, such as image and speech recognition, natural language processing, and game playing. Other types of AI models, including decision trees, Bayesian networks, support vector machine, each with its own strengths and weaknesses, and are used in different types of problems and applications. Now let's look at autoregressive models together. Autoregressive models are a class of statistical models that use the previous values of time series to predict the future values. The basic idea behind autoregressive models is that the current value of a time series is a function of its past values. In other words, the model assumes that the future values of the time series are dependent on the past values. Autoregressive models can be represented mathematically as a linear combination of the past values of the time series. The most common type of autoregressive model is the autoregressive integrated moving average, or also known as ARIMA. It's a model which is a combination of autoregression, differencing, and moving averages. The autoregressive component of the ARIMA model captures the relationship between the current value of the time series and its past values, while the differencing component is used to make the time series stationary, and the moving average component captures the short-term fluctuations in the time series. Autoregressive models have wide range of applications in various fields such as economics, finance, engineering, and environmental sciences. In economics and finance, autoregressive models are used to forecast stock prices, interest rates, and economic indicators such as GDP and inflation. In engineering, autoregressive models are used to predict the behavior of dynamic systems such as vibrations in structures and performance of control systems. In environmental science, autoregressive models are used to forecast the weather, water levels, and air quality. The popularity of the autoregressive models is due to the ability to capture the complex dynamics of time series data and their simplicity in terms of specification and estimation. Hopefully this has been helpful. So the basic autoregressive model is a linear model that predicts the value of a variable at time t based on the past p-values. Now let's look at non-linear autoregressive models. Non-linear autoregressive models are a class of statistical models that extend the non-linear autoregressive models by permitting for non-linear relationships between the current values of a time series and its past values. Non-linear autoregressive models are used to capture more complex dynamics in time series data that cannot be adequately modeled using linear autoregressive models. One common type of nonlinear autoregressive model is the nonlinear autoregressive exogenous or NARCS. So the NARCS model uses a nonlinear function such as neural network to map the past values of the time series and exogenous variables to the current value of the time series. Another type of nonlinear autoregressive model is a nonlinear autoregressive moving average or NARMA. NARMA models are a generalization of linear autoregressive moving averages or ARMA models that allow for nonlinear relationships between the current value of the time series and the past value. NARMA models use a non-linear function such as a neural network, a map uh, the past values of the time series and the error terms to the current values of the time series. Non-linear autoregressive models have a wide range of applications in various fields such as economics, finance, engineering, and environmental sciences. As I discussed earlier, the popularity of the nonlinear autoregressive models is due to the ability to capture complex dynamics of time series data and that cannot be adequately modeled using linear autoregressive models. Hopefully this is helpful. The recurrent neural networks are a type of neural networks that are particularly well suited for autoregressive models. They have a memory that allows them to retain information from the past and use it to make predictions. Let's look into some actual application of recurrent neural networks in the practical world. The natural language processing is one area where RNNs are commonly used. These models are sequential nature of language. In the industry, RNNs are used for tasks such as language translation, sentiment analysis, and text summarization. For example, companies such as Google, Microsoft, and Amazon are using RNNs in their machine learning and machine translation. Speech recognition is another area where RNNs are used, and these are for temporal dependencies in speech signals. In the industry, they use to build automatic speech recognition or ASR systems that can transcribe speech in real time. For example, companies like Apple, Google, and Amazon, such as Siri, Google Assistant, or Alexa, are the examples to respond to the user queries. RNNs are well suited for modeling time series data as well, as they can capture the temporal dependencies in the data. In the industry, RNNs are used for tasks such as stock price prediction, energy consumption forecasting, and demand forecasting. For example, companies such as Uber, Lyft, and Airbnb use RNNs to forecast the demand for their services and to optimize their pricing and resource allocation. Okay. The basic RNN architecture consists of series of interconnected nodes called neurons that are arranged in a chain-like structure. Each neuron in the chain receives input from the previous neuron and passes its output to the next neuron. Limitations of basic RNNs. Basic RNNs have a number of limitations, including inability to capture long-term dependencies and the vanishing gradient problem. These limitations make it difficult to train RNNs and use them for autoregressive modeling. Long short-term memory or LSTM. It's a type of RNN that is designed to overcome the limitations of the basic RNNs. It has a memory cell that permits it to retain information from the past and use it to make predictions. LSTM architecture consists of a series of interconnected memory blocks, each of which contains a memory cell and 3 gates. The gates control the flow of information into and out the memory cell, permitting the LSTM to selectively retain or forget information. Gated recurrent unit. I have published on the epidemic of loneliness. I would suggest you to go and look at the application of the gated recurrent units. In that, in quite depth, I have discussed how the GRUs work. GRU is a type of RNN that is similar to LSTM but has a simple architecture. It has a memory cell that allows it to retain information from the past and use it to make predictions. GRU architecture. The GRU architecture consists of a series of interconnected memory blocks, each of which contains a memory cell and two gates. The gates control the flow of information into and out the memory cell, permitting the GRU to selectively retain or forget information. What are the applications of autoregressive models? Let's look into few of these in a little bit more depth. Autoregressive models have a wide range of applications in healthcare, including disease prediction, patient monitoring, and treatment planning. Here is an example how autoregressive models are used in healthcare provision. So I have witnessed that firsthand. Patient monitoring and prediction of adverse events. The autoregressive models are used in patient monitoring to predict the likelihood of adverse events such as sepsis, cardiac arrest, and respiratory failure. These models use data from electronic health records or EHRs, including vital signs, laboratory tests, results, and medication orders, or to predict the likelihood of adverse events. For example, Rothman Index, an autoregressive model developed by ParaHealth, is used in hospitals across the United States to predict the likelihood of adverse events and to identify patients who are at risk of deterioration. The Rothman Index uses data from EHRs or electronic health records, including vital signs, lab test results, and nursing assessments to calculate the score that reflects the patient's overall condition. The score is updated in real time and is used to alert clinicians when the patient's condition is deteriorating. Autoregressive models can also be used to predict the likelihood of other adverse events such as hospital admissions, falls, and pressure ulcers. By predicting likelihood of adverse events, clinicians can intervene early and prevent these events from occurring, which can improve patients' outcomes and reduce healthcare costs. Autoregressive models are a valuable tool in healthcare provision. They can be used to predict the likelihood of adverse events, permitting clinicians to intervene early to prevent these events from occurring. This can lead to improved patient outcomes and reduce healthcare costs, as I have mentioned earlier. So, the summary of the first few slides is autoregressive models are a powerful and flexible class of statistical models that are used to predict the values of a variable based on its past values. RNNs, and in particular LSTM and GRU, are particularly well suited for autoregressive modeling and have been used to achieve state-of-the-art results in the variety of tasks. Let's look into transformers together in a little bit more depth. Transformers have become popular architecture in the field of natural language processing, or NLP, and have been widely used in automated translation systems. The key innovation of transformers is this use of self-attention mechanisms, which allow the model to weigh the importance of different words in a sentence when encoding and decoding the text. This allows the model to capture the long-range dependencies and context of the words in the sentence, which is crucial for accurate translation. The transformer architecture was introduced in the paper Attention is All You Need by Vaswani in 2017, and the book Deep Learning for Natural Language Processing by Hazarika Zhang and Peoria in 2018 provides a detailed explanation of the transformer architecture and its application in natural language processing. Google Translate, Facebook's machine translation system, and Amazon's machine translation systems are examples of AT systems that use transformers as their primary architecture. Google Translate uses transformers which improve the quality of translation, particularly for languages with complex morphology and syntax. Facebook's machine translation system uses transformer learning, where a transformer model is first pre trained on a large corpus of text and then fine tuned on a smaller dataset of parallel translations. Amazon's machine translation systems use multi source translation, where the model is trained to translate from multiple source languages into a single target language. The book Neural Machine Translation by Cohns and Knowles 2017 provides a comprehensive overview of the history and development of machine translation, including use of transformations in AT. The book Transfer Learning in Natural Language Processing by Rudder, Plank, and Bingle 2019 provides a detailed explanation of transformer learning and its applications in NLP. Transformers have become crucial architecture in the field of automated translation and have been widely used in automated translation systems by companies. As I mentioned earlier, the use of self-attention mechanism in transformers allow the model to capture long-range dependencies and the context of the words in the sentence. So the basic transformer architecture is consists of series of encoder and decoders, as we have been discussing in earlier lectures. Layers, each of which is composed of a self-attention mechanism and a feed-forward neural network. The self-attention mechanism permits the transformers to attend to different parts of the input sequence and weight their importance accordingly. The transformers for music generation. I would suggest you to look at suno.ai and then you will know what I mean. But let's look into this in a little bit more depth. Transformers have also been applied to the field of music generation. The key idea is to use the self-attention mechanism in transformers to model a long-range dependencies and structure of music. One example of using transformers for music generation is a work done by Huang et al. In 2018 in the paper Music Transformers. The authors proposed a transformer-based model for generating music with long-term structure. The model is trained on a large dataset of MIDI or MIDI files and uses a hierarchical attention mechanism to model the structure of music at different levels, such as measures, phrases, and sections. The model is able to generate music that is coherent and musically plausible. Another example is a work by Dhariwal et al. In the paper Jukebox, a generative model for music. It was published in 2020, whereas the Music Transformer paper was published in 2018. The authors proposed in the second paper a transformer-based model for generating music with high fidelity and long-term coherence. The model is trained on a large dataset of audio files and uses a multi-scale vector quantized variational autoencoder or VQVAE to model the audio at different levels of granularity. The model is able to generate music in a variety of genres or genres and styles and with a high level of fidelity. Transformers have been copied and applied in various areas of music generation and have shown promising results in modeling a long range dependencies and structure of the music. Hopefully this has been given you some ideas. So do look at suno.ai, where you can make your own music and songs. The music transformer is a transformer based on the model that was developed specifically for music generation. Again, I'm not going to go into detail. It does deal with the relative attention. So the application of transformers in music generation, as I have just discussed in quite depth, so I'll just rather read it. I would suggest you to read this and have a look at the transformers which are used in music generation. Now let's look into the MuseGen or MuseGAN. MuseGAN is a generative adversarial network that was developed specifically for the music generation. It is capable of generating high quality musical compositions that are coherent and musically pleasing and has been used to create a variety of musical styles and genres. So let's look into Muse GAN architecture to understand a little bit more in-depth comprehension of this topic. The key idea behind Muse GAN or Muse Generative Adversarial Network is to generate music in multiple tracks such as drums, bass, and melody simultaneously. The model uses a differentiable composition module to combine the generated tracks into a single piece of music. The composition module allows the model to capture the interactions and dependencies between the different tracks and to generate music that is coherent and musically plausible. The model also uses a multi-scale discriminator to evaluate uh, the generated music at different levels of granularity, such as notes, measures, and sections. This allows the model to capture the long range dependencies and structures of the music. MuseGAN is a GAN based model for music generation that is able to generate music in multiple tracks. The model was introduced in the paper MuseGAN Multi Track Music Generation with Differentiable Composition by Dong et al. In 2018. Hopefully, this has helped you in understanding more about what MuseGAN is. The applications of the MuseGAN are MuseGAN has a number of potential applications, including the creation of personalized musical compositions, the generation of background music for games and videos, and the development of new musical styles, and the list goes on. It also has the potential to revolutionize the way that music is composed and produced by making it possible for anyone to create high quality musical compositions with minimal effort. So, the transformers are a powerful and flexible class of neural networks that are particularly well suited for natural language processing and other sequence to sequence tasks. They have been shown to be effective for music generation and have the potential to revolutionize the way that music is composed and produced. MuseGAN is a powerful and flexible GAN that is capable of generating high quality musical compositions that are coherent and musically pleasing. As discussed earlier, it has a number of potential applications as we have discussed. I would suggest you to look at the generative adversarial network in more depth so you understand how this works. Happy learning. Hopefully, this has given you a comprehensive idea. Before we close this, let me tell you a little story about generative adversarial networks. So now I'm going to share with you something that I have experienced personally. So this starts with the synthetic customer data, which I generated by a GAN model that was trained on a real data set of customer information, such as demographics, purchase history, and customer feedback. The GAN model was able to generate new synthetic customer data that was similar to the real data but not identical, so to keep the anonymity. The synthetic data was generated for various purposes, such as testing and training customer service systems without compromising the privacy and security of the real customer data. And I did this project in 2015 in Oklahoma City. Another example of the use of GANs in customer service was the generation of personalized customer responses. That was the next stage of the project that I am discussing at this moment with you. GANs was used to generate personalized responses to customer inquiries and complaints based on the customer's information and history. The GAN model was trained on a dataset of customer inquiries and responses and was able to generate new personalized responses that were similar to the real responses but not identical. This actually improved the efficiency and effectiveness of the customer service system by providing personalized and relevant responses to the customers. So, in reality, GANs have been applied to the field of customer service in various ways, such as the generation of synthetic customer data and generation of personalized customer responses. The use of GANs can certainly improve the efficiency and effectiveness of the customer service system by including key performance indicators and the potential outcomes. Wish you best of health. Happy learning.